Okay, guys. So the other day we were talking about centripetal force. We were looking at some examples of forces that can act as a centripetal force. And the first example we looked at was how friction acts as a centripetal force if you are turning an unbanked or level corner. Okay, so like at any corner, any intersection in town here, when you make a turn, it's friction that allows you to turn that corner, okay, and travel in the arc that gets you around it. Okay, and we looked at that as a kind of an example of this. Okay, we said that for any circular motion, Fc is really like our net force. Okay, net force is normally calculated by going mass times acceleration. Now, if something is moving around and around in a circle, the acceleration and the net force both point which way? In or out? In, yeah, towards the center. Centripetal means center seeking, okay? And that means that for Fc, it's mass times the centripetal acceleration, okay? Which we also write this way. Okay, v squared over r calculates centripetal acceleration. So our formula for centripetal force was mass times speed squared divided by r. Okay, everybody with me there? Okay. The next thing we talked about was how centripetal force is not a force in and of itself. In the same way that net force is not a force in and of itself, it's the sum of all the other forces that are acting. Okay? With centripetal force, it's actually a little bit easier because centripetal force is usually provided by one thing. Okay? So there isn't centripetal force as its own item, it's something acting as the centripetal force. Okay? And the first example we looked at was how friction could act as a centripetal force in an unbanked corner. Okay? And so all we did was say, this is kind of like our sum of all forces step. I just have to figure out what's providing the centripetal force in this example and set those two forces equal to each other. Okay? And then I can look at their formulas. So mu times the normal force equals mv squared over r. Okay? Or something along those lines. Everybody all right with that? So that was unbanked corners. At the end of the day, we started talking about banked corners, banked curves, and how when a plane tilts its wings, okay, what it's doing is using the force that the lifting force that the wings exert. By tilting the plane, you're getting some of that lift now not acting straight up and down, but now having a component of it that's directed into the center. So when a plane banks its wings, like you can see in this diagram here, the wings produce a force this direction, always perpendicular to the wings. But now there's a part of that force that is directed straight upwards, and there's a part of that force that's directed inwards towards the center of the circle. Everyone with me there? Okay, so that blue line then is our centripetal force. It's a component of the angle of bank and the lifting force of the wings. When a plane does that, now not all of the lift is directed upwards. So what's the plane also going to do while it turns? It's going to drop. Yeah, okay? Because when the plane is level, the lifting force offsets the force of gravity. Okay? But when the plane banks, now there's only this much, the red line, force upwards produced by the wings, and it's not enough to overcome gravity, so the plane also starts to drop. Okay? It's not really a big concern for us in terms of circles, okay? But important if you're piloting a plane. Because you have to understand that when you bank the wings, you're also going to lose altitude. It is something you have to keep track of. All right, then we talked about how a banked corner works on the ground, okay? And we're talking about the NASCAR corners and how steep they are, okay? NASCAR corners are incredibly banked, because what they allow, what the banked corner allows to happen is for the car's inertia as well as the normal force of the road to have a component that acts back towards the middle. Because really, all a banked corner is an inclined plane. Okay? Now, it's an inclined plane that goes like this. That's the best three-dimensional drawing I've ever made. Okay? But as you're going around this corner, okay, if this is just an inclined plane, if something is just sitting here, okay, then you've got our usual FG, okay, FN, and F parallel. Okay? If you just set something on the corner, you just set something on an inclined plane, and it's going to want to slide down, okay, towards the center. But if that object is moving around on this sloped surface, that triangle changes. And it changes because normal force will get bigger. Okay? What makes the normal force get bigger? Because, like I said, on a normal inclined plane where there's only movement up or down as opposed to around, gravity is the biggest side. Okay? Normal force is smaller, and F parallel is here. Okay? But when the car is moving, normal force gets bigger.
Feels like the cars move faster, so that's for the friction.
Even if this was frictionless, let's say this is frictionless, so we're not even going to bring friction in, but you're on the right track. Which way does the car want to go as it goes around the corner? Straight. What keeps it from doing that? Yeah, the normal force. The surface keeps it from doing that. As I go around this corner, okay, in this direction like this, what the car wants to do is kind of go this way. It wants to go out of the circle because of its inertia. And the faster you're going, the more of that you're going to have. So the harder the surface will have to push. The surface, though, normal force, can only act perpendicular. Okay? So it pushes like that. Now, when it does that, it'll have a vertical component and a horizontal component. So it'll have different colors here. Actually, I should draw that in the right place. So it'll have a vertical component that is here. That's going to offset gravity, because obviously no matter how hard we go around the corner, we're not falling through the corner. Okay, so it's offsetting gravity. And then this side is directed back towards the center and acts as our centripetal force. Okay? Now, look at what that means for the angle of bank. So here's theta. It's the same as this angle, the angle of bank. The more I bank that corner, what happens to FC? It gets bigger. Okay? If I make this angle bigger, okay, so I spread this triangle from here to now here, what just happened to the opposite side? Got bigger. Okay? Got bigger and bigger. So the more I bank it, the bigger it gets. Okay? The more centripetal force I get. The problem is that the more I bank it, the more the car also wants to do what? Yeah, slide down. Okay? Like if you put it up like this on its side, you'd have to go fast enough that you would overcome gravity and not fall, which you could do. It's like that ride that I showed you, Gravitron. Okay, like that. Okay, if you go fast enough, sure, you can overcome it and be pinned to the wall. But you have to go pretty darn fast. And it wouldn't be very comfortable for a driver. Okay, driving around a totally vertical corner. Okay, but they do get banked pretty steeply. And the more I bank it, the more centripetal force I get. Okay? So, obviously in NASCAR, the purpose of banking the corners is to make them be able to take the corners faster. Okay? For civilian use, the purpose of a banked curve is to produce a curve that is safe no matter what the road conditions are. It eliminates the need for friction. Okay? By banking the corner, now you can see that in here, I don't have force of friction labeled anywhere. Okay? I'm imagining that this corner is covered in perfectly frictionless ice, which means if I go the right speed, I stay right in the corner. If I go too fast, I'll go out, and if I go too slow, I'll slide in. Okay? Now obviously, you're never going to have a corner covered with perfectly frictionless ice. Okay? There's always going to be a little bit of friction, but that speed that's posted on any exit ramp is the safe speed, regardless of how slippery or dry or whatever it is. Okay? That speed, it can be safely negotiated no matter what. Okay? And that has to do with the angle we bank it. Now, do we bank them very much? Not usually. And the angle of bank actually changes a bit throughout the corner for a couple of reasons. Drainage, okay? But also, you're usually going pretty fast when you come into the corner, okay? That's where people are most likely to lose it, is right at the beginning of the ramp. So that's usually where the bank is a bit more pronounced, okay? As you're coming out, like especially if you think about this one out here, okay? When you first come into that corner, it's banked pretty steeply, but as you get to the point where you're merging, it's almost flat again, okay? Now, once it turns flat, that's when you want to put on the power and merge properly, unlike the person in front of me yesterday, okay? Who just about got us both killed because they didn't accelerate.
So what angle do you think that one is? Because it feels like we're getting thrown around.
If you take it really fast, yes. Okay, so obviously now we know Nick's driving habits, okay? But it's not banked very much. Yeah, and that's why you feel thrown out. Your inertia still wants you to go in a straight line, and that's out of the car and off the corner. So it isn't banked very much. Most bank curves are gonna be 5 to 8 degrees, and not much more than that. Beyond that, they actually are pretty steep. I know 10 degrees doesn't seem very steep, but it is. Okay, it's, you know, if you go to 10 degrees, you're looking at about an 11% grade. Okay, most roads have to be less than that. So when you go in the mountains, sometimes you'll see those, you know, the hill signs, and it'll have a percentage on it. Okay, that's basically telling you how many percent of vertical that hill is, and you almost never see one more than 12. Okay, because it's not safe to go up or down. Okay, on a road that steep if the conditions deteriorate. Okay, so is that sort of making sense how that works? Okay, so we want to bank these curves for the purpose of making them safer. It's not about making them faster. Okay, exit ramps and things like that are built just to guarantee safety. All right, so here's what we need to look at. What are the things that can affect how quickly you can take a banked curve? Okay, so if I'm looking at the things that could affect the speed at which I can take a banked curve, what are some of them? Without friction. Let's ignore friction. Okay? Actually, no. But it's a good guess. Mass is usually what people guess first because they think, well, heavier means more. It means more for friction. But even with an unbanked corner, mass actually cancels out. Mass will cancel out here as well.
Like with the force of gravity, would that change anything?
Well, no. It won't, because the force of gravity and the normal force are related to each other by mass. So it's the same factor affecting both, so it has no effect. Yeah.
So it'd be like where you are on the angle?
Where you are, so how big the angle or how far up the hill?
How far up the hill?
How far up the hill? That's radius, definitely. Okay, radius would affect it, right? What else? We just talked about it. Yeah, the angle of bank, that's going to affect it. That's it. Those are the two things. Okay? Those are the two things that can affect how fast you can take a banked corner, how big the corner is, and how much it's banked. Okay? Because here's how it works. This here, this green side, is my centripetal force. That's the component of normal force that is allowing me to stay in the corner. Okay? It is affected by the angle and essentially gravity. All right? So my centripetal force, okay, is mv squared over r. Okay? That's the opposite side to this angle. Agreed? Okay. What's the adjacent side to this angle? Force of gravity. Okay, so I'm going to do this. I'm going to divide this by this. That would give me that. Do you agree? Opposite divided by adjacent would be the tan of the angle. Okay. So when I do this, James, you mentioned this. You said mass. What's going to happen to mass if I divide these two things? It'll cancel out. That's important. Think about it. How many speed limits are there on a corner? All right, if mass mattered, how many speed limits would there be on a corner? A lot. Because you'd have to have one for every mass, which would actually require you to know the mass of your vehicle. Anyone know the mass of their vehicle? I don't. I have no idea what it is. And it changes depending on how many people are in it. So, no, we don't want to have mass be a factor here because then it could change. Okay? A fully loaded truck and an unloaded truck. Okay? One person in the vehicle, 5 people in the vehicle, it makes a difference. Okay? So mass is going to cancel. Okay? And what I'm going to be left with is v squared divided by r times g gives me the angle of bank, or the tan of the angle of bank. This is the same formula that road designers use to determine their angles and their radius. Okay? They know how much room they have, so they've got the radius. Okay? They can manipulate the angle just by the construction of the corner, and that will help them to determine what speed is best for that corner. Okay? This formula is on your formula sheet. Okay? And it is the formula for a banked curve. Okay. Now, you are never going to have to derive this formula as I just did. Okay? You always have that formula on your formula sheet. But you do need to understand how the bank curve works. Okay? We have to understand that the angle of bank affects the speed, how far up the corner, the radius affects the speed, okay, at which that bank curve can be taken. Right? And also gravity. Not the force of gravity, but the acceleration due to gravity. Okay? A bank curve, if I took a bank curve from Earth and put it on Mars, it would work differently. Okay? It would have a much lower speed that I could take it at because there'd be less normal force, okay, from the weight of the car. Okay? Everybody all right with how that works? All right, so this is just all that derivation that we went through. Okay, so on a real bank curve in the real world, obviously we also have a force of friction that is contributing to staying in the corner, right? Because it's never perfectly frictionless. And you can see that that acts up and down the plane just like F parallel does, but it would have a component that would be directed towards the middle. That's a terrible color. Okay, that would be directed towards the middle that would be affected by that same angle of bank. Okay, so yes, friction does play a factor. We're never going to do a question where it does, but obviously in the real world it does play a factor. Okay, but you don't get to use all the friction. Okay, most of the friction is keeping you from sliding up or down the corner. Okay, and you only get a component of it acting towards the middle. Okay, acting as part of the centripetal force. Okay, so if we wanted to determine the angle at which a frictionless curve should be banked for a speed of 35 meters per second and a turning radius of 550 meters, okay, we would just use this formula. All right, so we know the speed, we know v is 35, we know r is 550, we know g is 9.81, okay, so we would just manipulate so that we would have theta equals tan to the minus 1 of v squared over rg. Okay, and so when we do that, we would have, for this one, tan to the minus 1 of, like we say here, 35 squared over 550 times 9.81. Okay, and that'll give us our angle of bank to be 13 degrees. That is a very steep exit. okay with that? Sorry, I want to get a bank curve question here first. Then we're going to come back and look at these other ones. Wow, was that far? Was that far? Still. Okay, I don't have a bank curve. We're going to come back to that. Okay, there's a couple here I want to look at. Couple of things to remember about rotations per minute and hertz. This comes up quite a bit in this unit. Remember this formula from the first day? Period is 1 over frequency. Okay, remember that period is seconds per cycle. Okay, how long it takes to make one complete revolution or orbit. Okay, and that frequency is cycles per second. Okay, which is also sometimes written as hertz. Okay, so just so you know what you're being given, right, in a question. Okay, and we also talked about this formula, V equals 2 pi r over t, which is what our lab was about yesterday, which we also said could be written 2 pi r times f, because f is 1 over t. All right. Okay, so we got a pebble stuck in the treads of a tire, okay, and it is 36 centimeters or 0.36 meters from the center of the hub. So what did they just give us? Radius, right. Okay, it takes just 0.4 seconds for the wheel to make one revolution. What is the speed of the pebble at any instant? Okay, so I was given period, 0.40 seconds, because they told us how long it takes to make one circle, and they told me the radius, 0.36 meters. Can I find the speed? Okay, so that's involving this formula from the other day. Okay, I've got radius, I've got period, looking for speed. So 2 pi times 0.36 divided by 0.4. Make sure you're using the pi function, don't write 3.14. Okay, so that rock is moving at 5.7 meters per second at any one point along the tire. Now, as an application question, what's holding the rock in the tire? Yeah, it is friction. Okay, when a rock gets jammed in the treads of your tire, okay, you guys have all seen this, right? Like you look on the treads of your tire, you see a rock jammed in there. Okay, that rock is eventually going to come out. Right? If you go fast enough, okay, it'll fly out, and then it usually hits somebody's windshield. Okay, but it's stuck in there for now. What's holding it in there is the force of friction between the rubber and the rock. Okay, but at some point, the rock's inertia will be great enough that its desire to leave the circle will be greater than the tire's ability to hold it in the tread. Okay, where is that most likely to happen? As this thing goes around and around in the circle, at what point in the circle is it most likely to happen?
As it's leaving the ground.
Yep. Right here. That's where it's most likely to leave the circle. Because because this is actually a vertical circle, that's where it's going the fastest. And that's also where the tire's shape changes. When the tire hits the road, it squishes the tire a little bit. The treads can spread out a little bit, and there'll be less friction right there. So just as that rock gets exposed, that's kind of where the tire's trying to come back to its shape. That's where it'll spit out, which is why it always does this, okay, and hits the car behind, which is also why trucks have mud flaps, okay? They have mud flaps. They keep the vast majority of those rocks from being able to be flung behind them and hitting other people. If those are worn, and they're only this long, they are useless. Okay? And all that stuff will get out underneath. But that's the purpose of mud flaps. It keeps that stuff from being shot out, okay, where it can hit other people. Okay. I want you guys to try number 2. Okay, I'm going to give you a few minutes to work on number 2. They're giving you 2 pieces of information, and they're asking you to calculate the speed. Yep. Okay. Okay, so we have this pulsar, which is a collapsed star. Okay, so if it doesn't go like supernova, it just kind of collapses on itself. Okay, then it becomes this super dense thing that spins around and actually emits light. Okay, like pulses of it, which is why it's called a pulsar. Okay, so it only has a radius of 16.1 kilometers. So imagine something as massive as our sun, same mass as our sun, but only 16.1 kilometers in radius. So it would fit inside the city of Calgary easily. Okay, but it is as massive as the sun. Spins really fast. Okay, really, really fast. Okay, it spins at a rate of 716 hertz. So they gave me radius, 16,100 meters, because I'll probably want it in meters, okay? And they gave me what? Is this period or frequency? It's frequency. 216 hertz. So imagine this thing is spinning around and around 216 times every, sorry, 716, no, it's even more, okay? 716 times every what? 716 revolutions per second. Okay? Imagine Calgary spinning around and around. 716 times in a second. Everything would be like destroyed, liquefied. Okay? Yeah. Would be good. So, this is what we have. We've got radius, we've got frequency, and we're being asked to calculate V. 2 pi r f. Okay, we could go 2 pi r over t, but that brings in an extra calculation. Then I got to go 1 over 716. I don't want to do that. Okay, so 2 times pi times 16,100 times 716. Okay, that's going to give us this speed right here. 7.24 times 10 to the 7th. To give you an idea, the speed of light is 3.0 times 10 to the 8. This thing is spinning so fast that objects on its surface will be experiencing the effects of relativity. Okay, that means like time slowing down for them. Well, they don't really know it, but it appears to us like they would be slowed down, right? Because they're going close to the speed of light. Very, very fast. Okay. Questions on how that formula works? Everybody good with that one? Pretty easy formula. Yep. Alright, I want you guys to try those 2. Okay, they just involve centripetal force, mv squared over r. Okay, so all of these ones involve this. All right, so for question number 1, okay, we've got our mass is 7.5 kilograms. We know that as it spins, it's moving at 365.9 meters per second, and its radius is 73.7 centimeters, which of course we have to convert to meters in order to make this work. So all we're doing is plugging numbers into the formula. We don't even have to manipulate it. Okay, we've got 7.5 times 365.9 squared divided by 0.737 okay, as our radius, and that should give us our 1.36 times 10 to the 6 newtons. Okay, that's a lot of force. Okay, but those fan blades are spinning really fast, so they have to be built out of very, very strong material in order to keep them from flying off. All right, how many people have done number 2? Okay, so let's have a look at 2 then. All right, so we know the mass of the pebble in number 2, okay, and so it's 0.0021 kilograms, okay, and we know that it's 23 centimeters from the hub of the wheel, so 0.23 meters, and we know that the centripetal force is 0.660 newtons. We're looking for V. So on this one, we do have to do a little bit of algebra, but nothing we can't handle, okay, where we have to manipulate this formula, mv squared over r, but we manipulate for V. So we're going to multiply both sides by r, divide both sides by m, and then square root to get V. So what we'll have here is the square root of, okay, 0.23 times 0.660 divided by 0.0021, and that should give us 8.5 meters per second as the speed of the pebble in the tire. Okay, that is a very common manipulation of that formula. Okay, we very often are asked to solve for speed in centripetal force problems. Okay, so being able to do that manipulation is pretty important. Questions on either one of those? Okay. All right, this is an unbanked corner. Okay, remember that in an unbanked corner, the force of friction is providing the centripetal force. It's not banked, so it's flat. Okay, see what you remember from the other day. See if you can solve this one. Okay, unbanked corner, we're trying to figure out how fast this vehicle can take the corner. Okay, so our givens in this question are the mass, 1,500 kilograms. Okay, we're also told it's an unbanked corner, which is why we had this reasoning earlier. Okay, we know the radius of the corner is 40 meters, and we know the coefficient of friction is 0.6. All right, so we're going to go back to this. Our centripetal force is being provided by the force of friction, so they're equal. That means that mu times the normal force equals mv squared over r. Because this is an unbanked corner, normal force is actually equal to what force? Force of gravity. So I can simplify this. Well, maybe not simplify, but substitute, okay, this. All right, now we were talking about this earlier. Mass is on both sides. What does that mean? Mass is going to cancel, which means that for an unbanked corner, mass is irrelevant. Okay, this is about the surfaces coming into contact with each other. Okay, so mass is going to cancel, and I'm trying to find the maximum speed. So I'm going to multiply both sides by r, and I'm going to get that v equals the square root of mu g r, or as we said before, mugr. Okay, all right, so the square root of mugr will give me v. That will be 0.6 times 9.81 meters per second squared times 40 meters. Square root of 0.6 times 9.81 times 40. All right, so the maximum speed that corner can be negotiated at is 15.3 meters per second. Actually, I think there's only 2 significant digits, so it would just be 15. All right, everybody okay with that? I cannot remember the last time the unit exam did not have a problem involving an unbanked corner as the first question. Okay. All right, I want you to try these. These are all unbanked corner questions. See how we do with those. Let's just try 1 and 2 for now. And see how we do with those. Watch out for the trick they're trying to play on you in question number 2, where they give you the speed in kilometers per hour as you need it in meters per second. Divide by 3.6. So we've got Edmonton Oiler who's got a mass of 100 kilograms. Been using this question for so long that I've watched them go from being god awful terrible to now what they are. First place, Alright, this used to be like a depressing question, because it would remind me of how bad they were, but then times are better. Alright, so we got mass equals 100 kilograms. We know that the radius of the turn is 7.17 meters, okay? And we're looking for the coefficient of, we're looking for the speed if the coefficient of friction is 0.80. Now, when you actually turn with skates, certainly there is an element of friction there, but it's also about getting the edge of your blade to actually cut into the ice and create like a lip, right, that your skate sits in, right, when you're actually turning. So have you ever seen, like, that's why they have to flood the ice, right? It gets so many big cuts in it from people turning on their, making their turns or whatever, that they need to fill them in again so that the ice is actually flat. Right, so when they make this turn, it's not just about friction, it's also about actually cutting a groove in the ice with your skate. Okay? So what we're looking at is that we're going to say it's just friction, and that's providing the centripetal force. Okay? So we're going to have mu times mg, the normal force, equals mv squared over r, and we're going to be manipulating for v. M's going to cancel, r is going to come over here, and we're going to square root. So v will equal the square root of 0.8 times 9.81 times 7.17 meters, right, which should give us a speed of 7.5 meters per second. Okay, questions on number 1? Okay, how are we doing on number 2? How many people have done 2? Okay, let's have a look at 2 then. All right, so number 2, same thing. It's still an unbanked corner, so we still have the force of friction providing the centripetal force. Just this time they're asking us to calculate mu, and they're giving us speed instead. All right, so we know that the radius of the turn is 100 meters. Okay, we know that the mass of the car is 1,200 kilograms, although that's irrelevant. Okay, we're not even going to need that number. And we know that the speed is 95 kilometers per hour, okay, divided by 3.6 for our purposes. Okay, so we're looking at 26.4 meters per second. I'll keep all the decimals in my calculator though. Okay, so we're looking for the coefficient of friction. So mu times m times g equals mv squared over r. Force of friction equals centripetal force because it's providing the centripetal force. So to calculate mu, we're going to divide both sides by m times g. Okay, m cancels. Now, where have you seen this combination of variables before? V squared over r times g. We actually just talked about it at the beginning of class. It's also how you calculate the angle of bank for a banked curve. What do these two formulas have in common? They're always calculating the variable that keeps you in a what? In a circle. Okay, for a banked curve, it's the angle of bank. For an unbanked curve, it's the coefficient of friction. It's not by accident that those things are affected by the same variables in the same way. All right, so when we're plugging in our numbers here, okay, we've got 26.4 squared divided by 100, okay, times 9.81. Right, and when we do that, we should get 0.710 for our coefficient of friction, which is pretty darn sticky. Okay. All right, how are we feeling about that? All right, I'm going to give you a 5-minute break, but remember, breaks are different now. You have to stay here for your break. Okay. Thank your friends who wrecked the bathrooms for that one. Okay, you got to stay here. Okay, but I'll give you 5 minutes. We'll be back 1:30. And we're gonna do a couple more. Okay? So take a little break here. Okay, so on this one here, our givens are that we know the radius, 125 meters, okay? And we know the angle is 20 degrees. Okay, so we've got a bank curve. We know that the bank curve formula is this. So anytime they mention angle of bank, you can go straight to this formula. It's the only time you would use it. Okay, we don't use that formula for anything else in this unit other than bank corners. So I am looking for the maximum speed. So I'm looking for V. So I've got to multiply both sides by R times G. So I'm going to have tan of theta times R times G equals V squared. I just want V, so I'm going to square root that. So that will leave me with the tan of 20 times 125 times 9.81. Right, that should leave us with 21.1 meters per second. Okay, everybody all right with that? Right, so bank corners are really not too tough. There's nothing to do except use this formula and manipulate it for whatever it's looking for. You're never going to get a bank curve formula that is more, or bank curve problem, sorry, that is more than, here's the formula, find one of the parts of it. Okay. All right, so this is actually the from the digital workbook that I gave you guys earlier. Okay, so there's a bunch of different types of questions in here. Some of them are very easy. Okay, so this is an unbanked curve question like we've been working on, right? There's some in here that are a little bit trickier. And it's mostly just the context that makes them a bit tricky. Okay, but there's a few good ones in here. For right now, I want you to try number 6, solving for coefficient of friction on that. Okay, so on number 6, our givens are the mass, 925 kilograms, although that's probably going to prove to be irrelevant. Okay, we know the speed, 25 meters per second. We know the radius is 72 meters, and we're being asked to calculate the coefficient of friction that would be possible here to keep it from skidding. So mu mg, the force of friction, equals mv squared over r. Divide both sides by m times g. Okay, so we'll get g on the bottom, the m's will cancel. Okay, and we get that mu is v squared over r times g. So that'll be 25 squared divided by 72 times 9.81, which should give us our 0.88 for our mu. All right. Your final exam date has been set. Yeah. They always try and get that out right before parent-teacher interviews. So it's January the 24th. I think that's a Monday. Okay. It's at 9 a.m. and it'll be in one of the rooms down this wing. Probably this one, but I don't know that for sure. Okay. Just so you're aware, it's January 24th. I think they posted this on the school website as well. You can check it out if you want to. But obviously it's a long way off. But if you're planning anything way ahead of time, plan around that. It's kind of important. You have to write it. Yeah, all that good stuff. All right, if I can get you guys to clear off your desks, I gotta wipe them down before my next class.